The tutorial today is going to be more introduction to the homework. So I already uploaded to the Moodle the second homework. We're going to include one question of Monte Carlo simulation, which is what you did with Ido. And the second one going to be related to what we're going to do now. So this is going to be like the first part of the question to like kind of help you, So we're going to talk about the Heisenberg model. But before that, we're going to do some general reminder of spin and addition of spin, because like sometimes some students like you have some gaps, so that's going to be like a few minutes. If someone gets bored, like you have to phone. I don't know. So spin. So more general spin and angular momentum. So for those of you who remember from like quantum mechanics 2 and stuff, you have the operator for the spin, you have operator for some orbital angular momentum, and you also can define a generalized angular momentum in case you have both. Or so you have you usually have two quantum numbers that relate to the spin. So one comes from the eigenvalue of the operators S square. So if we have an eigenstate with the two quantum numbers, which are S and M, the eigenvalue of this operator going to be H plus square S plus 1 on S M. And the other one is for the projection of the operator of the spin on the z direction. So the eigenvalue of that relates to the quantum number n, which is H bar m Sm. So if we have either like more than one particle or more than one type of angular momentum, for example, if we have particles that have both spin and orbital angular momentum, or we have two particles that each of them have spin, we can define the generalized angular momentum, which will be just, for example, S1 plus S2. If we have, we're going to talk mostly about spin, so I'm going to use S. So if S1 and S2 have like two quantum numbers each, S1 and M1, etc. So we're going to, let's do addition. So if we start from state S1 and M1 and another state of S2 and M2, we're going to move to a new basis of generalized spin with S1, S2, J, and M. So those will be, let's call it small. So those will be the new quantum numbers. which are going to be correspondingly the eigenvalues of j squared and jz. And those are the same S1 and S2 that we have here. We're usually not going to write them. Like I'm usually going to write it as just G and M because I'm lazy. And S1 and S2 are not going to change, but they are still going to be diagonalized in the new basis. So we still keep them. So we move from 4 quantum numbers to another 4 quantum numbers. Because they still good quantum numbers. Okay, so now the question is, first of all, what are the values of those J and M, and how are we going to move from one basis to another? So J1, J going to be between S1 minus S2 to S1 plus S2, and M going to be between minus J, J with like integers gap. So, differences, integer chunks. So, what?
ב-M הזה צריך להיות שווה, אבל לא. מינוס J קטן שווה, קטן שווה.
Yeah, so for example, if I have 2 electrons, so I have S1 equal S2 equal half. The new generalized spin going to be equal either to the difference between them or the addition of them, so J either going to be 0 or 1. If J equals 0, M also equals 0, and if J equals 1, M can be equal to either 0 or plus minus 1. Okay, so let's say we know what the quantum numbers are. Now we want to write the explicit eigenstate. So I have a state J and M, also S1 and S2. As I said, I'm not going to write it. And I want to write it as a linear combination of the old basis, the basis of S1 and M1 and S2 and M2. So I'm going to have S1, M1, and S2, M2, and I'm going to have coefficient for, let's say, with some general coefficient for each value of M1 and M2. So this will be C of M1, M2, and J and M. So you know those coefficients, they're called Krebs-Gordon. M1, M2, and J and M. You can also add here like S1 and S2. It's going to be like the function of all the parameters. Just, yeah. So here in the sum, we're going to have M1 and M2 because S1 and S2 are constant. And then, for example, if you look at the case that we saw for 2 spin half fermions, so this is like an example. In our example, you probably don't really need those coefficients. We have, as we said, we have 4 states overall for the new basis. So j equals 0, m equals 0, j equals 1, m equals 0, j equals 1, m equals -1, and j equals 1, and m equals 1. So those going to be super linear combination of the states of S1 and S2 equal half, and M12 equal plus minus half. So overall also 4 states. So through the tutorial, I'm going to refer to M equal plus minus half, like in the case of S equal half, as up and down, just for convenience. So if j equals 0 and m equals 0, what we're going to get, this is like a normal result, yeah? So we have up and down, minus down and up. So we can check and see that we have m1 equal half and m2 equal minus half, so it's overall 0. And because we subtract the 2 states, we're going to get also 0 for the total spin. So this is for the first one. The second one going to be the same one plus. So again, m1 and m2 going to cancel each other, but the overall spin in that case is going to be 1. For m equal -1, both spin going to go down. For m equal 1, both spin going to be up. And those have name. This called triplet, and this called triplets. So this is like a super trivial, relatively trivial example. But the same, you can use the Clutch-Gordon table thing to find like every combination that you need. I think you can usually like use like Wolfram or something now, so or like homework. Okay, so this is addition of angular momentum. Now we talk about the Heisenberg model. And then we're going to get to the question. So I think the closest thing that you saw so far in StatMech was the Ising model, where you have each time like you sum over couples of spin, but it's kind of a one-dimensional problem because the spin are always like scalar. So then in the Ising model you don't have like spins in different directions. You only have like one component. So the Heisenberg model is kind of a quantum 3-dimensional version of Ising model. So you have a coupling coefficient, and you have Si and Sj. Where now Si and Sj are going to be vectors. So S have 3 components, Sx, Sy, and Sd. You can also, of course, have external magnetic field, which we are not really going to do, but it exists in the model. I think people usually choose like h in the z direction, and that's going to be like SIZ, but in general it's going to be that. And so this is basically what you would see in like quantum mechanics course when you have like Hamiltonian, just any Hamiltonian that have multiplication of spin. So this is more like a quantum mechanics problem. The only difference is now we're going to have, of course, many particles, and this sum going to be all over the nearest neighbors, spins. So this is like, so this is similar to that.
זה תמיד יהיה עבור השכנים הקרובים ביותר המודל הזה, או שזה יהיה...
I think if you define not with nearest neighbors, I think it will be like a different model. Like you have all different models that are like the kind of Ising model or the kind of Heisenberg model, and you just name all of them. I'm not sure. So similar to the Ising model, we have the coupling coefficient J. And then if J is positive, it's going to be ferromagnet, and if J is negative, it's going to be antiferromagnet. So if J is positive, it means that all of the spins want to head to the same direction. And if J is, so the ground state energy of the system would be where all of the spins head to the same direction. But if J is negative, so the spin want to be like opposite direction. So if you have like a complicated system with a lot of spins, it's not very trivial to know what's the ground state energy of the system, because you know, like some of the spins want to head here, some of the spins want to head here, so it's kind of a more complicated problem. Okay?
זאת אומרת, כשזה מינוס אז אנחנו לא בהכרח מקבלים את אותו כיוון, אבל זה כאילו לא בהכרח שכולם יהיו בכיוונים מנוגדים, זה כאילו יהיה פשוט ערבוב בין כל הכיוונים.
If J is positive. Yes, we have minus something positive.
כן, ואז כאילו הם יוכלו בכל מיני כיוונים, ולא בהכרח כיוון.
No. If J is positive, it's like what we intuitively usually think about spin models, so they want to head the same direction. If J is negative, so this overall coefficient is positive, and then they want to be in like opposite direction, because we want to minimize the energy. So then we're going to have this potential mass.
שם, ואז כאילו יקרו שם. מתי בסוף שהם רוצים להגיע לאנרגיה מינימלית? זה לא שכולם יהיו בכיוונים מנוגדים. בזה ש-J הוא שלילי.
Yeah, and of course, if you have a magnetic field, so this becomes even more complicated problem, and a lot of fun. So this is the model, and now we're going to introduce the question. So we have a system with 3 spins, S1, S2, and S3, and they are coupled to each other with, so S1 and S2 are coupled with some coupling coefficient called K, and S2 and S3 and S3 and S1 are coupled with a different coefficient called J. And basically what we want to do, we want to first write the Hamiltonian, and then find the eigenstate and the eigenenergies, which is what we always do. Okay, so the Hamiltonian, we don't have external magnetic field, so we can ignore this term. And from here we see that we have 3 terms for each interaction. So let's start with K. So minus K multiply S1 and S2. Then minus J multiply S2 and S3 and S3 and S1.
triangle means? What with triangle means? למה ציירת את זה בצורת משולש?
Because that's how they could, like, I could draw it like that, but they are connected to each other in that way.
Okay.
So we have two ways to solve this, probably more than two ways, but two ways that I thought about. So one of them we are actually going to use, the other one for those who want to be adventurous, I don't know. I'm going to explain shortly in the end, and also going to appear in the Moodle and etc. But let's start with the simpler one. So we have multiplication of vectors, which is not something that we really know how to work with. So we want to go to something that we know how to diagonalize, like S1 square or SZ, or something that is more that we know what to do with. So if you look at the term over here, so as we said earlier, we can define S12, just an operator, that is S1 plus S2. And then S12 square will be S1 square plus S2 square plus 2S1, S2. And now we can use that to rewrite the expression over here as half S12 square minus S1 square minus S2 square. Okay, and now it's going to be much easier because we know the eigenvalues and eigenstate of S1 square and S2 square. We soon going to know also for S12 because we saw how to do addition of angular momentum, and this is much easier problem to solve. So for this term over here, we're going to do something different, so something similar. So let's take out S3, so this is going to be S1 plus S2. So S1 plus S2 we already defined as S12. And then this is overall. We're going to define S1, 2, 3, which is S12 plus S3. And then this is going to be half S1, 2, 3 square minus S1, 2 square minus S3 square. And now the Hamiltonian is minus k over 2 S1, 2 square minus S1 square minus S2 square. And same here, minus j over 2. Questions?
רגע, מי זה S1, 2, 3 שהגדרת פה? זה בעצם הסכום בין.
It's that. Okay, so for example, for S1 square, it's easier. It's very easy. We wrote it 10 minutes ago on the board. We know that the eigenvalues are going to be h bar square, S1, S1 plus 1. I think I go out of the gamma, but it's okay. So we know the eigenvalues, but for S1, S12, and S23, we need to find the new quantum numbers. So we start with S1 equal S2 equal S3 equal half. So for S12, we have two options. Like we said before, we just integrate into that. So S12 equal either 0 or 1. And now we're going to add also S3. So if S12 equals 0, we only have one option to add S12 and S3. So S123 going to be half. Right? Because it's go for minus absolute value of minus half to half. So we only have one option. If S12 is equal 1, so S123 going to be either half or 3 halves. So we're going to have two options. And for each one of those options, the value of the quantum number related to the projection on the z direction going to be, so for if it's equal half, m going to be plus minus half. Same here. And here it's going to be plus minus 3/2 plus minus half. So those are all of our options.
Just an
You know there's video, right?
לא תמיד קצת מטושטש לפעמים.
Okay. No problem. Okay, I probably shouldn't have deleted the last one. So let's write it here. So first we want to find the energy, and for that we only need the quantum number, so we don't need the eigenstate yet, so we only care about the value of S12 and S123. So for S1 square and S2 square, the eigenvalues of those we already know. It's going to be 3/4 h bar square, right? Half multiplied by 3/2. Here. Okay, now for S12. So now I need to look at like specific cases because S1 and S2 and S3 are all fixed. They can only have one value, but S12 and S123 have different options. So let's start with the simpler case where S12 is equal half. So case 1. So the expectation value of S12 square going to be 0, and for S123 going to be also 3/4 multiplied by h by square. So E equals minus k/2, 0, 3/2 h by square minus j/2. mistake in the lecture notes. I have to fix it later. So this is overall 3 over 4 h plus squared k plus 3 over 8 j h plus squared. Okay, this is 1 answer. Is 2. So now S12 equal 1. And let's start with S123 also equal half. So the expectation value of S12 square going to be 1 multiplied by 2h plus square. So this is a 2h plus square. And if we go back to the energy, so there's going to be minus k over 2, 2h plus square minus 3 over 2h square minus j over 2. And this stay the same because it's 1, 2, 3. Sorry, this stay the same. And here I did a mistake. Sorry. Yeah, this is 3 over 4. And I also took accidentally this one to B, so this is just 0. So 3 over 4 h square minus 2h square minus 3 over 4. And this is overall. Now let's go to the last case, where S123 equals 3 over 2. So now the expectation value of S123 going to be 3 over 2 multiplied by 5 over 2, so 15 over 4, and then the energy okay, so these stay the same. This 15 over 4h plus square minus 3 over 4 no. Okay. So those are the energies. And now what we need to find is the eigenstate. So we need a wave function. So
רגע, זה 15 חלקי 4 h עוד?
כן.
כמה ל-15?
3 חלקי 2 כפול 5 חלקי 2. So we kind of already found the eigenstates, right, when we specify the quantum numbers. So in that case, the eigenstate is S12 equals 0 and S123 equal half and S1 equal half and etc. But we want to find the eigenstate in the old basis, which is like the physical basis of S1, S2, and S3. So we have, of course, a few ways to do that. So one is to use directly the Clebsch-Gordon coefficients. And the other one is what I'm going to show now. So let's choose this state. So we have for S1 to 3 equals 3/2, we have four eigenfunctions for each value of M. So, if you remember, when we talk about the addition of angular momentum, the value of M need to be the sum over, so like M of 1 to 3 have to be the sum of M1 plus M2 plus M3. So it's usually not very helpful because you have different combinations of that, but in the case, if we choose M equal 3/2, there's only one option to write that state. So for S1, 2, 3 equals 3/2, and also M equals 3/2, the only option to get that state is if all of the spins head to the z direction. So this the only matching state will be up, up, and up. So this will be M1, M2, and M3. So of course I also have hidden here the value of S1, S2, S3, and all of that, but you know, ignorant. Okay, so this trick we can only do for 3/2. Probably also for minus 3/2. It's going to be just the opposite option. So if M equals minus 3/2, it's just going to be all of the spins heading down. But what we're going to do for the case of M equal half or minus half, because this is no longer useful. So what we're going to do is to use the raising and lowering operators. So if you remember, for spins, we can define the operator S plus minus, which will be Sx plus minus I Sy, where Sx and Sy are the x and y component of the spin operator. And if we use, for example, S plus on states, I'm just going to write in general. If you use S plus minus on a state with S and M, you're going to get some factor of h bar square root of S plus 1 minus M plus 1 minus 1, and the state is going to be S M plus minus 1. So S plus is going to take M to M plus 1, and S minus is going to take M to M minus 1. So if we use S minus on that state, we're going to get something that gives us like another eigenstate of the system. So since we have three different like parameters, the degree of freedoms for S1, 2, and 3. We define S, that's S plus minus 1, 2, 3, which is S plus minus 1 plus S plus minus 2 plus S plus minus 3.
מה זה הפסיק הזה מעל ה-S?
Stick. They're all like
operators.
In the same way, kind of like we define S1, 2 and S1, 2, 3. So now we can use it once on the left and on the left hand right of this expression, and once on the right side. So and see what we get. So let's take first the left and right. So S1, 2, 3 on S1, 2, 3 and M1, 2, 3 equals 3 over 2. So if we just want the minus. So H bar 3 over 2 multiplied by 5 over 2 and 3 over 2 multiplied by half. So overall square root of 3 H bar, and now M going to be M minus 1, so this is 3 over 2 and half. So this is going to give us whatever going to come out of the right hand side. It's going to give us the corresponding to the eigenfunction of M1 plus 3 equal half. So now let's do the other side. So S1 minus plus S2 minus plus S3 minus multiplied by all 3 spins are heading up. So S1, for example, S1 on up and up, going to change only the M1 component. So this is going to give us H bar down, up, and up. Okay, and the same for S2 and S3. So this is going to be up, down, down, up, and up, plus up, down, and up, plus up, up, and down. So overall, we compare the two results, and the states S1 to 3 equals 3 over 2, and M1 to 3 equal half, is equal to 1 over square root of 3, and then that. So in the same way, which I'm not going to do because we understood the concept, you can do the same for, you can either use, you can either use again S minus on that to get the state for M1 to 3 equal minus half, or you can use that state with like S plus and get the same. Or you can use Tרגול. But that's not fun. Okay. So, okay, that was fast. So we can say that we found for this relatively simple system of space spin, we find the eigenstates and we find the eigenvalues. So what you're going to do in the homework is to take a system that instead of one triangle, you have a lot of triangles, and try to solve that. So, what you're supposed to do, they give you like instructions in the question. You're supposed to use variational method. So, for those of you again who don't remember, I will just do a super quick reminder. So, the variational method, as you did in like quantum mechanics courses. So, the first thing that you do is to guess a wave function. So, you guess like a trial wave function. The general purpose of the method is to find like the ground state. So, this is what we're going to look at. So you guess a trial wave function, and the second one, you find the expectation value of the Hamiltonian. So if you guess the trial wave function, let's call it psi, like psi t. So you calculate psi t h psi t, and the assumption of the variational method is that that thing going to be larger or equal than the actual ground state of the system. So what you're going to need to prove is that the number of triangles, which is going to be n, multiplied by the ground state energy of one triangle is larger than the actual ground state of the system. So you guess a function. Again, you have a bunch of instructions. If you have a problem, you can write to me, but this thing is like relatively straightforward, and you calculate that and you show that it works.
רגע, אז עוד פעם, אמרת שאנחנו נראה עם ההנחה הזאת? כאילו אמרת שיש את השלישי, אמרת שאת ה-N הזה שם, ואמרת שנעשים...
You're going to have everything in the question. I'm just going to give like a brief reminder to those who don't remember. Yeah. So, the last thing is, so we had earlier the Hamiltonian. So we just write I'm not sure those were the indices, but you understand the concept. So another way to approach this problem is to do it to write the Hamiltonian as an explicit matrix, which is the way that you wanted me to do. But this is going to be 8 by 8 matrix. So most of the matrix elements going to be 0, but it's still not a very nice way, I think, to work with it. But basically, if you want to do that, you use the fact that I can write instead of do the addition of angular momentum, you can write the actual product of S1 and S2 or any other couple. So you have S1x, S2x plus S1y, S2y plus S1z, S2z. So you have 3 elements for each multiplication. So the SD element, we know how it works. So this is like the easier part. And for x and y, we can use the s plus minus operator, which is sx plus minus I sy. So for each state, for example, up, down, up, we're going to have 8 of those, so we need to take into account all of them. But because we know that, like, if I use s minus 2 on that state, so the second spin, m2, is already minus half. So I cannot make it lower than that. So this is going to be 0. And the same thing if I use s1 plus or s3 plus. So you see that automatically most of those matrix elements are going to be 0. So you can already like think ahead and say like, oh, those are only going to be like those and those non-zero elements. So you rewrite that with those operator and you calculate the elemented state. I'm going to put on the model, I think I did the example where like k equals j, but it's like obviously the same concept for any case. And then you get a matrix, and then you can diagonalize the matrix and do everything that we did. Maybe some of you will prefer that, I don't know. So just so you know, that's also a thing. So, okay, and I think that was all the tutorial. We didn't
אז דבר ראשון, אולי נזכר משהו סבבה דברים, אחרי זה לא צריך לדבר על עקרונות באולי ולשיטה לנו.
כן, אז מה שקורה שעושים את כל העניין של כשאני כותבת את הספין הכולל של קומבינציה ליניארית, אז הפרמות של הדבר הזה היא כוללת את המפת כבר כעקרון היסוד. המצבים שאתה מקבל הם כבר כוללים את הדבר הזה.